Okay, hello everyone. It is my great pleasure to welcome Blakesley Burkhart. Blakesley is an all-star. She is an assistant professor at Rutgers and a research assistant professor. Is that what you're called?
Associate research scientist.
Yep.
An ARS.
At the CCA. She is one of the most productive, if not the most productive scientists I've ever met in my entire life. She is the only person who I know who has gotten both all of a Packard Fellowship, a Sloan Fellowship, and an Annie Jump Cannon Award. So she is a very decorated general. She works on magnetic turbulence at all scales in the universe. One of my favorite things about listening to talks by Blakesley is that she is immensely creative. She applies different theoretical frameworks to a whole expanse of problems. And so it's always an exciting adventure to hear her speak about things. She did her undergraduate at University of Louisville. Louisville, yeah, that's new. I was going to butcher that.
You have a Louisville, Colorado. How do you say it here?
Louisville.
Oh, we say Louisville.
Yeah, we enunciate. She was at University of Wisconsin-Madison for graduate school. And she was an Einstein Fellow and in their Institute for Theory and Computation Fellow at Harvard. She is an incredibly excellent speaker, and I'm very excited to hear her talk about magnetic turbulence today.
Now. You really set me up. Well, yeah. Yeah, it's actually just such a pleasure to be here in person, and I have to thank also Mitch for really just sticking with me through the chain of 30 emails to make this talk happen in person, because I really wanted to come to Boulder. It's my first time here visiting the department and enjoying the beautiful mountains and the beautiful campus. And I'm just really happy to be here. In person, it's actually my first in-person colloquium in 2.5 years. So it's just, thank you all for having me. And I'm really excited to tell you about a couple different I'd say progress points we've made in terms of analytic calculations of star formation, in terms of explaining star formation observables. Primarily, this will be in the context of local Milky Way clouds, because that's where we have the resolution to really resolve the star formation rates, the star formation efficiencies, really actually in a resolved sense, dig down on where the young stars are forming and at what rates they're forming, what mass function they have, et cetera. So how can we as a theorist, right, that is motivated by observations, that wants to match observations of star forming regions, how can we test that with a model? So I'm going to be talking about a particular class of star formation models called turbulent regulated star formation models. Maybe some of you are familiar with that, and maybe it just sounded like I spoke a foreign language. What is turbulence? What does star formation matter? So I'm going to kind of take it a step back and walk everyone through how we approach studies of star formation from this turbulent paradigm. And one important way we do that is through the use of numerical simulations. And so here I'm showing one of my simulations that is using a fluid MHD equation, so the magnetohydrodynamic equations with self-gravity. So we evolve these simulations with under the conditions of self-gravity and supersonic motions. So we form these beautiful filamentary features that are formed by shocks moving around in the fluid. And of course, also self-gravity aggregates the material together. And eventually, in the very densest regions here, we start to see the formation of stars. And this looks all very pretty and nice, but actually under the hood, there's a lot of assumptions about how the stars form. And the equations we use, are they the right equations? Are they oversimplified? So I'll touch a little bit on that as well. So the outline of my talk, if it will advance. It doesn't want to advance. It loves this slide. There we go. This slide is so much more boring than the last one. Didn't want to advance. So outline here, just to give you an overview of how broad I'm going to be in the talk. So I want to really take a step back. Why do we care about star formation? What's the problem? Why is it interesting? How is star formation linked to turbulence, right? Some of you may never really encounter turbulence except on an airplane and in some uncomfortable bumps, or maybe when you stir your milk in your coffee in the morning and you induce mixing to rapidly diffuse the milk into the rest of the coffee. You know, those are kind of our daily experiences of fluid turbulence. A screen just went off. I guess that's okay. Okay. So, you know, how does the formation of the sun and other stars, how is that linked to turbulence? And then I'm going to talk about coming up with various like simple calculations, analytic calculations for how you link turbulence with star formation, and then how you make predictions for that, right? So I'll talk about kind of the previous literature where we've gone with this. And then finally, a good theorist always should provide some comparisons with observations. And in my case, also simulations, so I'll also show that towards the end. And I'm happy to take questions throughout the talk as well. So why should you care about star formation? Well, there's lots of different reasons. And one of them is that, you know, stellar evolution is very well established, right? It's like a triumph of like modern 20th century astrophysics is coming up with, you know, understanding of once you form a star based on its mass, what will its evolutionary track be? How will it spend its life living as a star and also as a star that's dying? What will happen to it, right? So of course, like especially for a lot of people in the audience, the massive stars are extremely exciting because those are the progenitors of compact objects, black holes, et cetera. And so this evolutionary pathway is very well understood. But how does that star get its start in life? How does it form out of a gas cloud in a galaxy, or even a cloud that's ejected out of the galaxy? There can be many different star formation pathways. That process is not well understood at all. It's very complex, in part because we don't have a good understanding of fluid turbulence, right? So these clouds are very turbulent, as I'll motivate in a second. And we really don't have a first principles understanding of turbulence. Therefore, we don't have this first principle view of how you form stars. There's lots of other applications for star formation, right? So compact objects, progenitors being one of them. But of course, people like on larger scales, galaxy scales, they're more interested in feedback and how that can affect the galaxy evolution. And the formation of these beautiful kind of plumes that can come out of galaxies. These are winds that are driven primarily by explosions of supernova, again, from these massive dying stars. So, you know, coming up with how you connect this star formation rates to mass outflow rates in galaxies, again, connects to star formation. And then, of course, planet formation, right? If you don't have star formation, you don't have planet formation. So planet formation is a really exciting topic right now. And so again, this is all connected to how stars form. So if we don't have an understanding of star formation, we're kind of missing the first link in all of these really interesting areas of astrophysics. There's a lot of interesting questions surrounding star formation. I'm not going to talk about all of them in this talk. One that I will address is something called the star formation efficiency problem. This is a very old problem in the sense that you can do very easily a back of the envelope calculation to show how fast should stars form, like what rates should they form at, and at what efficiency do you convert gas mass in galaxies into stellar mass. So the natural time scale of the star formation process probably should be, the first guess would probably be the free fall time, right? So you can estimate how long it will take a gas cloud of a certain density to collapse, right? And all you need for that is the density itself. So if we can take like an average ISM molecular density, 17 per cubic centimeter, we can easily calculate the expected time for collapse. It's around 8 times 10 to the 6 years. And then if we add up all the molecular gas that's roughly sitting at that density in our galaxy, then we can just simply divide the mass by the time scale, right? And get the expected amount of star formation based on just pure self-gravitational collapse, right? So the total molecular mass for the Milky Way is something like 2 times 10 to the 9 solar masses. So if you take that mass and divide it by the time scale, you get around 250 solar masses per year of stars that should be forming if just free fall collapse is the only kind of physical process considered. Well, of course, the observed star formation rates, you can ask Erica all about how you observe star formation rates in the Milky Way and other faraway galaxies. they're all much lower, especially locally. They're more around 1 to 2 solar masses per year for our Milky Way, right? So there's about 1% efficiency of star formation versus the expected star formation that we see. So something is slowing down star formation. Something is making star formation less efficient. So another way to put this star formation efficiency problem is the problem isn't really how you form stars, right? The problem is how to not form stars. How do you prevent the gas from becoming gravitationally unstable? Right, and this problem now, this is like the back of the envelope calculation that was done, many decades ago, and now observations have really shown in like an incredible way that this efficiency of around 1%. So I showed kind of the fiducial numbers for the Milky Way, but this actually holds for external galaxies in very different environments. It also holds for high redshift galaxies, at least the ones that we've observed so far, right? So JWST is going to be incredible for this. So I love this plot. It's a kind of complicated plot, so I'll walk you guys through it. It's originally from analysis by Krumholtz, Deckel, McKee, 2012, and it's kind of a retake on what's called a Kennicutt-Schmidt relation. Kennicutt-Schmidt relation is on the y-axis here, you have the star formation rate surface density. And on the x-axis, usually you have surface density of gas. So this could be like solar mass per parsec squared. Here it's also then divided by that free fall time. So it's very much like the efficiency argument that I just made, taking a mass divided by a time scale. Here it's a surface density, but basically it's telling you the same thing. So this line here is that 1% conversion between just free fall collapse and then the actual rate of star formation that's observed. What makes this plot, I think, amazing, that I love about it, is that here you have these local Milky Way clouds, right? So that's this kind of resolved blob here, where you can actually resolve very nicely the star formation rate, surface density, the gas surface density, et cetera. So that's why you have a lot of data here. And as you go out in these points, these are individual galaxies, some of them at high redshift, very, very different types of galaxies, starbursts, at low and high redshift. You can see that, well, if I asked you, identify in this plot the high redshift starbursting galaxies or the more quiescent galaxies or the Milky Way clouds, you would say, well, the Milky Way clouds I can tell because they're at low star formation rates, but actually all of these very different galaxies at very different redshifts all seem to have around 1% efficiency with the same kind of scatter around that 1% line. So environment of the galaxy actually doesn't seem to set the efficiency, right? So it's something perhaps deeper related to the fluid properties in molecular regions where these stars form that sets this 1% efficiency. And I find this just amazing. This 1% turns out to be important for a lot of applications, right? So for people who aren't necessarily interested in star formation, but they want to study galaxy formation. So for example, like cosmological simulations like Illustris TNG, they can't resolve star formation in their simulations. So they kind of just plug in that 1% by hand. All right, once gas gets above a certain threshold, we call it star forming gas. It forms at a 1% efficiency. Why? Because observations. So this is an observed star formation law, and we want to try to explain it. Why does nature form stars at around 1%? Well, maybe based on the title of my talk, you're like, well, I bet it has something to do with turbulence. So before I get into that, I want to take just a small detour and talk about what is turbulence and maybe give you a little physical intuition about why it might be important for regulating the star formation process. And one thing you can already right away think of is that turbulence should give some additional supportive terms to the collapsing cloud, right? So the toy problem I just talked about, we just had self-gravitational collapse, right? Well, there could be additional supportive terms like magnetic pressure and also thermal pressure. There can also be a non-thermal pressure that can be provided by turbulent motions, right? And a great analogy I like to give, again, I'm going to give coffee as the example because I love coffee, right? If anyone uses a French press, right? When you pour the water in, you've got the coffee grinds in there, and you wait for things to settle down before you press, right? So you actually don't, what you wouldn't ever do is stir things up again and then try to press it down, right? When you induce those turbulent mixing motions, right, the coffee grinds and the water there's eddies there that now provide some additional pressure that push back against when you're trying to push down your French press. Right, so turbulence can provide some additional pressure support that prevents star formation. Right, so how do you get the turbulence? Well, there's a couple different ways you can get turbulence, right? So once the stars form, the feedback processes, the winds, the jets, and of course supernova can then feed into that turbulent motion in the galaxy. You can also get turbulence from larger scale processes. So gravitational instability, if you're dealing with a disk galaxy, is one. An MRI can give you turbulence. There's many different very large scale kind of galaxy kiloparsec scale processes that can provide the turbulent motions. So the turbulence is there somehow, and it's providing this pressure support. So this is kind of the key, one of the key ideas behind this turbulent regulated star formation model is that turbulence provides some sort of supportive motion for the cloud, right? So again, you know, this is just basically what I already said. There's also another interesting part of the puzzle in that, you know, there's also seemingly potentially a threshold for star formation, right? Because all the local star formation, all the star formation that we observe, local and also at high redshift, forms in molecular gas, right? And so there might be some kind of threshold that's set in order to get that gas to be dense enough, to be cold enough, both to be molecular as well as to become gravitationally unstable. So turbulence can probably also help in setting some kind of threshold there for star formation. So that's like the general cartoon picture. But I might even want to take a step back a little further and just tell you what is turbulence, right? Because I've given like an analogy of an airplane and coffee, and you still might be like, well, I don't quite get it. If you talk to an engineer and you ask an engineer what is turbulence, I guarantee you they're going to start talking about Reynolds numbers, right? And so I think a really nice way to think about what is the onset of a turbulent fluid and why is the ISM naturally turbulent, right? If you look at your momentum equation, just for hydrodynamic fluids, you have these two terms, like an inertial term and a viscous term. And in the equations, both the hydrodynamic equations and the magnetohydrodynamic equations, you can find these dimensionless numbers that give you really nice insight into what's happening with the fluid. So if you take the ratio and like just do some dimensional analysis of the ratio of these inertial and viscous terms, you come to what's called the Reynolds number, which is dimensionless. So you have a dependence on the fluid velocity, the length scale of the system, and the fluid viscosity. And turbulent fluids all have high Reynolds numbers. In fact, there seems to be like a critical Reynolds number, you know, around 10 to the 3 or so, where you transition from a laminar to turbulent flow. So very, very high Reynolds number flows are almost impossible to keep laminar. There actually are some really incredible engineering experiments that try to increase the Reynolds number of the system and keep the fluid laminar and then study the transition between laminar and turbulent. But in general, without like very special conditions that you impose on the fluid, boundary conditions, it's almost impossible to keep that high Reynolds number flow laminar, right? So you naturally have this turbulent flow at high Reynolds numbers. Well, for astrophysical objects, right, the velocities and especially the length scales can be astrophysical. And so you can easily get Reynolds numbers of like 10 to the 8 or 10 to the 10 or so for interstellar medium type of objects. So we kind of naturally expect this turbulence to already be present in the ISM. And I really find just the fluid turbulence in interstellar objects and also in galaxies to be a fascinating topic in and of itself. So star formation is obviously the topic that I'm touching on today, but I wanted to point out to you that turbulence, and especially magnetized turbulence, so magnetohydrodynamic turbulence, ends up affecting a huge range of interesting physical processes. And I've talked with quite a few of you today already about some of these that are mentioned here. And again, today here, I'm going to focus on the star formation problem, but these are all you know, aspects of the problem that I'm interested in, the fluid turbulence problem. So, okay, back to our topic of star formation. Turbulence can be supportive, right? But it can also be compressive. And this is really where things get weird in the turbulent star formation paradigm, because the turbulence isn't just like moving around the fluid, but not really changing how compressed it is, right? So we have supersonic motions, compressible motions in the interstellar medium, which means you can have shocks. So on one hand, you can have an enhancement also of the star formation rates or star formation efficiencies because the turbulence is supersonic and compressible, right? You form shocks in the medium. And then, as I mentioned, you can also decrease the star formation rate because you have pressure support. So I want to give you a visualization of this. You might have noticed a movie just went off. So here's effect one. So here, this is a simulation that we've performed where we seed the initial density fluctuations here with driven supersonic turbulence. And then we turn off the turbulence completely and we turn on gravity, right? So this is a case where you have rapid collapse. So you have just this purely enhancement of the star formation rate because of the turbulent fluctuations, right? If you started with a different initial condition for your density field, like a spherical or a cylindrical, purely kind of smooth density field, you wouldn't have as much collapse as you would in this case, right? Because you've already seeded all of these really high density supersonically induced filaments, turn on gravity, everything just rapidly collapses on the free fall time, right? Because turbulence got turned off. So this is an example of where you can have enhancement of the star formation rate. And you see all these little blue stars that formed in the filament here because of the supersonic motions. Now, let me show you kind of an effect two, right? Where now we keep the turbulence on, right? So turbulence is allowed to stay on. Well, that means that that pressure support from the turbulent motions continues to act, right? Whereas in the previous case, it stopped. And you can see by eye, right? You don't have pure free fall collapse anymore because our turbulent driving is keeping these density fluctuations constantly moving. And there's always constantly some supportive action going on from them. And so you still form stars along these shocked filamentary regions, but the shocks also get disrupted as they're moving around and colliding with each other. And so in the end result of this simulation, where we keep the turbulence on, is that the star formation rate is suppressed as compared to just the case with gravity, right? So that's a little bit of a visualization how turbulence can both support and inhibit. So here we're driving the turbulence in Fourier space. So we have a particular set of wave modes that we drive on large scales. And then we allow that to evolve, cascade down. Yeah.
In your toy model of the free fall time, are you taking the free fall time, it has to be also supersonic?
No, so oh, yes, of course. The question was about the free fall time and if it was assumed to be supersonic. So the free fall time only depends on the density locally. So the free fall time will have, in a sense, a dependence on if a shock went through, because the shock will create a density enhancement, and that will make the free fall time shorter. So they are related, but the free fall time really just depends on the density. Yeah, so, this obviously becomes a big parameter space, right? Because you can have, let's say, different magnetic field strengths, different levels of compressibility, different parameters of the star forming environment. And so to that end, we've created a little project here to share simulation resources. It's at mhdturbulence.com. You can go there right now and start your download. Right after my talk, you can start to analyze some of the simulations similar to what I just showed you. And so the project is called CATS, the Catalog for Astrophysical Turbulence Simulations. And so we're sharing all these kind of simulations so you also can do your own star formation or turbulent kinds of research. So just a little plug for the CATS project. All right, that's enough simulation and motivating the problem, I think. So let's talk about how we might make a simple model for understanding how turbulence sets the star formation efficiency. So this is something that a lot of people have been excited about, right? Coming up with a good analytic testable model for star formation. And there's kind of two different approaches people have taken. So either from the bottom up, where you start from the molecular cloud physics, like the molecular cloud 10 to 100 parsec scales, or from galaxy scales, right? And so I think for the star formation efficiency, motivated by that plot from Krumholtz, Deckel, McKee, For the efficiency, it makes sense to really think about the cloud scales, like what's happening there, right? So what's happening with the turbulence. And this kind of approach that I'm going to talk about has like a very rich history in the literature, turbulent regulated star formation, and it's been used to describe all kinds of different things about star formation, not just the efficiency or the rate, but also like the initial mass function, et cetera. And really what it comes down to is actually a very simple result that the turbulence, the supersonic turbulence, sets a density distribution that is a log normal. Right. And so I'll show you a little bit about how this log normal, the properties like the width and so forth are controlled by the turbulence in a second. But just to give you an intuitive sense of this, right, if you have the density fluctuation set by a log normal, and you want to ask yourself, how much of my cloud, now that has this log normal density PDF, will form stars? All you need to do is figure out, well, what is like a critical threshold for star formation? What's a critical density for collapse? And then integrate that, you get a fraction of the mass that's going to go into stars. So you can then turn that into like a total mass, and also give it a time scale. And you can maybe choose some like normalized units. So you have like density divided by the mean density. And for a time scale, usually the natural time scale again is the free fall rate. So you can take that to be some as a function of density here. And then you can do this integral. So S here, I'm defining now as the natural log of the density divided by the mean density for the cloud. So you just integrate whatever that critical S or critical density is over your log normal, which would be this P of S here, and you're done, right? That's it. You've got your star formation efficiency or star formation rate, just based on this very simple integral over a log normal. All you need to do, right, is figure out what sets the threshold for collapse, right? The critical density. And I'll describe this in a second, what this is. And then you also need to know what sets the properties of your log normal, like its width and so forth. Cool, let's do that. What sets the log normal width? Yes, next slide is interesting, so it had trouble. So here's, this setting of the width of the turbulent compressible log normal PDF has been studied quite a bit. This is a nice visualization from Price and Federath with one of these very similarly driven turbulent boxes where you drive at the large scales, you develop supersonic motions. I think this one has like a Mach number of 10 or so. And then you see this development of the log normal, and people usually attribute this to the central limit theorem because you have all these colliding shocks in density space, and you naturally get this log normal PDF. And a few years ago, we did a lot of work on figuring out, well, how does the width scale with Mach number, right? And so this is all empirical based on simulations, but I think it makes nice intuitive sense, right? If you have one of these turbulent box simulations, and here's one that's incompressible, low Mach number, so there's no shocks, you get this kind of narrow PDF in terms of the density distribution. And again, this is natural log of the density distribution, just normalized by the mean density. It's nice and narrow. So you imagine like you have a threshold for star formation, whatever that is. Subsonic motions, because they're very narrow, they don't have that compressibility from like high Mach numbers. They're not going to maybe get over that critical density and form stars. Right, there's just not enough compression of the density to get you there. But if you now go to a higher Mach number simulation where you increase, let's say, the velocity or decrease the sound speed, and now you get these beautiful shocks and filaments that form. Well, now maybe some gas, because of the shocks, now gets pushed to higher density such that you now can start to collapse at least some of those dense features into stars. And you see just generally the width of the PDF will get broader, right? Because some gas gets pushed to more rarefied regions and some gas gets more compressed. And so you can keep doing this to higher and higher Mach number, right? And so what people have found is that the width, this little sigma here, depends on the Mach number squared, and also a little bit on how you drive the turbulence, right? So if you drive it fully like compressively, a compressive driving condition or a solenoidal driving condition for the velocity field, that can also affect the width. Great, so now we know what affects the width of our gas density distribution, and all we need to know now is what sets this where we should put our integral, right, for collapse. And so this is essentially like all the different literature papers that I pointed out when I started mentioning this analytic models. This is where they kind of differ, like what kind of physics goes into the critical. And so, you know, the supportive terms being the turbulent and thermal pressure, so that comes into the virial parameter, as well as how much compression you get from the sonic Mach number. Those sorts of terms enter into this critical density. And then, you know, you can also imagine, well, magnetic fields, of course, also will do some supporting of the cloud and could potentially change this critical density. And so, for example, like this paper by Padawan and Nordland, 2011, they have kind of a function that depends on the plasma beta. So the magnetic field can enter there as well. All right, but assuming we know the physics for setting a critical density, then we can easily compute this integral. And it's not pretty, you know, you take an integral of a log normal, well, you're going to get an error function and so forth. But anyway, it's finished, right? So we have everything parameterized here. The one thing that we don't maybe know so well, and that actually goes in as kind of a fudge factor here for the star formation rate, is, you know, how does feedback work? Right? Maybe not all of this gas past our critical density makes it into stars. Stellar feedback probably ejects some of it out of this region. So people usually put this kind of epsilon fudge factor in order to account for that. But anyway, this provides a really great starting point because it gives some testable features, right? So for example, really nice paper that kind of overviews all these testable features from Federath Klesson 2012. Are we back? All right. Great.
Thank you.
Hopefully you guys didn't miss too much. So I was just showing some of the predictions of the turbulent regulated models, right? So this is great because now observers, right, they can go out and test if these predictions hold or not. This is how what I'm going to show next. So these are observational data from a couple different sources, mostly for the sonic Mach numbers taken from Kainulainen and Federath 2014. Here we're showing the sonic Mach number and star formation efficiencies and star formation rates for local Milky Way clouds. So these clouds, you might notice some names that are familiar, like Taurus, Orion B, Orion A. Some of the other ones, you know, they don't even really have like good call names, but these are all local Milky Way clouds where we can actually, in kind of the best sense possible, resolve the velocities. This is from carbon monoxide observations, where we roughly know the temperatures from 12 and 13 CO. We can get the temperature and the velocity, so we can estimate a sonic Mach number for the cloud. And then for the star formation rates and efficiencies, we can actually go in and count the young stellar objects directly to get a star formation rate and estimate the cloud masses from a combination of gas and dust. So it makes sense to do this with local clouds just because that's where the most resolved view of the star forming properties is. So here, what I'm showing you is that there's not, you know, one of the predictions, of course, is that there should be a pretty strong scaling with sonic Mach number, right? And we just don't observe that. So the star formation rates and the Mach number, I mean, you know, if you took out Orion A, it really would just be completely a scatter plot. And then the star formation efficiency is really quite a scatter plot altogether. There's another problem that bothers me about these kinds of models, including the one I've made, I think a little bit of progress for matching the observations on, but still not 100% alleviated, right? Is that you're plugging in the efficiency here by hand. So this is typically called like a core efficiency, right? Because you're already in this dense gas phase. This gas is already going to collapse and form stars, right? So some amount goes back out from feedback, right? And so people, what they'll do is they'll tune this kind of fudge factor efficiency to match things like the Kennecott-Schmidt plot, right? But if you had to tune it to match, can you really say something predictive about the Kennecott-Schmidt relation? So I find that kind of a philosophical issue with these kinds of models, this tuning. And I don't have the full answer for it yet, but I think we're making some progress. And what is that progress? That's what I'll tell you in the last 10, 15 minutes so of the talk, is kind of a new analytic model that we've been working on. And the good news here for these kinds of theories is that actually the thing that people thought was really solid, right, which was the form of the density distribution, turned out to be not correct, right? So actually, instead of a log normal, what happens is as you go to higher densities, you actually form a power law in the density distribution. And this actually makes a lot of sense because self-gravitating gas, right, if you look at like a simple filamentary model, like an isothermal filament model, like a toy model, you naturally get a power law distribution for its PDF. And this is a nice summary cartoon from Hope Chen, who basically kind of compiled a range of different literatures and also did his own study where he shows essentially the atomic and like diffuse molecular gas is forming this log normal. But as you go to the higher density gas tracers or higher density dust tracers, actually these are low virial parameter. So gravity is dominating over the turbulent kinetic energy where this power law is forming. And so the power law is actually the appropriate form for the star forming gas in these kind of models. And there's also lots of other observations that I won't obviously go into all of them. I think these are really interesting though. The Herschel observations, this is dust emission observations published by Schneider et al. And there they showed, well, in quiescent clouds, local clouds again, like Polaris, where there's not a lot of star formation happening, you have the nice log normal in the dust emission. When you go to a cloud like Orion B, which is like bursting with star formation and even high mass star formation, you form this really beautiful power law tail there. So there's some link now, it's clear from observations between the presence and shallowness of this power law tail and the star forming environment. And of course, we actually see this also in simulations. And I think interestingly, the simulations, they really had to get into the era of adaptive mesh refinement in order to start resolving this power law tail and to get enough dynamic range in density, right? So when you turn on self-gravity, you need to also refine the collapsing structures. And when you do that, you do see this power law tail forming. And this is a paper from a couple years ago where we compared the slope of the power law tail, like as a function of time in these collapsing turbulent molecular clouds with time. So you can see you get shallower as the collapse proceeds. So you're building up more and more dense features as self-gravity takes hold of these supersonic filaments. And then there's also a nice correspondence here with star forming environments like Orion B or NGC 3603. Those are high mass star forming clouds. They have the kind of shallower power law tails. And we also found a really interesting dependence here on magnetic field, right? So you might expect the magnetic field, if it's higher, right, there's more magnetic pressure support, and that retards the collapse of the cloud, and that also makes it harder and harder to develop that shallow power law tail, right? And so here, the black points here are the transalphenic. So the magnetic field is essentially comparable in terms of its energy density to the kinetic energy. And so you see the power law tail becomes a lot steeper as compared to a case with a low magnetic field. All right, so we might want to include now this power law tail. And for first, to show you that this is a reasonable thing to now think about rather than scrapping this entire framework of these analytic turbulent models, right? We can go back to that same data set where I plotted the sonic Mach number. Now I'm plotting the measurements of the density power law slope. So again, this is like dust. This is dust observations here in emission. And so you can measure the PDF very easily. You can do some conversions between the 2D to 3D PDF that I won't get into, but basically you see, it's not a perfect correlation, but there's at least some now trend with the higher star formation regions all being more or less at these very shallow power law tail slopes, where the low star formation regions seem to have lower efficiencies of star formation. So this seems to be an interesting thing to look at, right? And also it makes sense observationally that you have a correlation with higher star formation rates with more dense gas. That seems to be something that's observed locally as well. So that would then translate into this shallow power law PDF. So we can really simply modify the existing framework. So now we can say, well, okay, we have a log normal, which is composed of the diffuse gas. And now we can have a piecewise PDF where around the critical density, or maybe even doesn't have to be linked to the critical density necessarily, we can start to develop this power law tail, right? And this power law tail will begin in the very dense gas because the free fall time is shortest there. And then eventually the gas will collapse on the local free fall rate to the point where you get this nice power law tail forming. So if you assume the PDF is continuous and differentiable, then you can derive the expressions for like the transition point and also the amplitude of where the log normal and the power law join. So the transition point is probably the most interesting here. It depends on the properties of turbulence set by the log normal width, as I discussed before, and then also how shallow that power law tail slope is. All right, so now we can go and redo the calculation, redo our integral for the star formation rates. So we can do this, you know, the kind of obvious way is to maybe, or the least parameterized way would be to consider maybe these critical densities as were done before, but now you also have a transition density. So you can do this really in a piecewise sense. Right, so this will end up getting really messy, but actually what we found from simulations is that there's no need to keep a separation between where you start your power law and where you join it to the log normal and how that approaches the critical density, because naturally the gas will collapse on its local freefall time very rapidly within a mega year, that these two densities become the same thing. And maybe you're like, well, of course they are, because the power law tail is produced by self-gravity. And that should be naturally a critical density where you see this power law tail forming, right? And so what makes the most sense is to say, well, okay, we start our critical density at the transition density. Those two things are essentially the same. This simplifies the problem a lot, right? Because now, you know, at least, especially observationally, we don't have to like, oh, what is the critical density? Like, how does it depend on Mach number and virial parameter? You can literally see observationally and also in our simulations, where does this transition happen, right? You can just fit a piecewise log normal plus power law tail, and, you know, just a least squares fit and actually derive it directly from the simulation or the observation. So this gives us the critical density almost just purely on the merit of what produces the power law. Just to show you quickly how the model compares to just log normal only. So log normal only, right? There's no, basically you just get a constant star formation rate for a given Mach number. Whereas when you add in the power law tail slope, at very steep power laws, there's essentially no difference, but as you develop that power law, you get an increase in the star formation rate. So that's a prediction, right? If you go out and you measure in local clouds, higher star formation rates, or maybe even within a cloud, individual areas where you have lower star formation or higher star formation, you should see a corresponding change in the power law slope in the density PDF, right? So the model is kind of inherently time varying with that power law slope as it varies. Right, and there's a really simple way to now divide the star forming gas from the non-star forming gas that could potentially help us with understanding how feedback should cycle gas between the two phases. Right, so we can also compute the fraction of dense self-gravitating gas just purely analytically by plugging in what sets the power law and what sets the log normal. My slide is not advancing. There we go. Right. Right. So we just have the mass in the power law. This is the star forming gas divided by the total mass. Right. That would give us the fraction of gas that's going to form stars. And then we might have now some unknown efficiency similar to the same problem as the previous models, which will then cycle gas between these two states. Right. So we can then empirically go out and try to find this in the simulations or maybe also in the observations now that we can again measure the power law mass in the observations and figure out like what is this core efficiency, what should it be? If we're able to parameterize that, then we're done, right? Then we could take this model and plug it right into a cosmological Zoom simulation and have a great working analytic model for star formation. I'm going to go a little faster. This is just us validating the analytic form for the self-gravitating gas fraction based on simulations, right? So I'm not just, throwing up this kind of ugly integral and its solution here. I'm actually showing you that, the lines here, which are the analytic function, they match the points pretty well, which are the MHD numerical simulations. So we've tested that this model with the assumption of continuity and differentiability of the PDF works pretty well. Okay, so it works great in the context of, gravity plus turbulence plus magnetic fields. But now, as I told you, the problem is getting that efficiency factor for feedback. So this is something that I'm working on with a student of mine now and some of our collaborators. These are not our simulations. These are simulations from Mike Grudich, which I think are just beautiful in showing how this is really important for the star formation efficiency problem, right? So here, these colored lines are the efficiency of these simulations that include all the relevant physics I've been talking about, plus wind and jet feedback, plus at the very, very end, supernova, right? And so if you compare that, the colored lines, to the black line here, this is a case with no feedback at all. So similar to the simulations I've shown you thus far, you can see that you really miss the efficiency altogether, right? You'll just continue to collapse gas without feedback until eventually it's slower than free fall, but eventually you reach 100% efficiency. So feedback's absolutely essential if you want to get an analytic model right for star formation efficiencies. So this is what my student Sabrina is working on. And so far she's studying this with simulations that touch on individual physics, right? And so she's really nailing down exactly what sets this core efficiency conversion from the power law mass to stellar mass. And so I can show you a little video of these simulations. So here on the top, we have just gravity, right? So of course it collapses on the free fall rate of the local density compressions. Here we have gravity plus turbulence, right? So again, similar to the simulations I showed you earlier, things are a little slower, but still pretty fast, too fast for the observations. Here now we add the same initial conditions, but now magnetic fields, and it's even slower. That's why the simulation keeps running. They stop at 20% efficiency. So there it stopped. And the slowest of all, right, is now where we have jet and wind feedback from the forming star. So you can see the jets exploding and pushing out their momentum and moving the gas around. And the efficiency, this is the integrated efficiency over the whole simulation lifetime. It's the slowest of all of them. So how do the PDFs look here? And how does that connect to the model? Right? Well, the gravity and turbulence in B field cases, or just pure gravity, they look exactly like you would expect now, right? Log normal plus power law, or in the gravity case, you just have these really beautiful booming power laws. When you turn on the jet and wind feedback, the cycling happens, just as we were hoping it would happen in the model, right? So now you push gas out of the collapsing portion of the PDF, and you develop all of this sort of non-log normal, very low density features in the gas PDF. So again, the analytic model, right, should be inherently time dependent, time varying, and you increase a lot of this diffuse gas from the cycling, which then reduces the star formation efficiency. So here's a plot of that star formation efficiency. And gravity and turbulence in red and green, they really overshoot the observations, right? So it should be around 1% at a free fall time. And then the magnetic fields and feedback cases are the lowest efficiency at all. This is the core efficiency that we're after. And on a free fall time, we actually match the observations pretty well so far. So people, observations, they estimate this like very, very dense gas core efficiency at around 20 to 50%, which is what we're getting here in our simulations. So this is exciting, and it allows us now, the very last thing I'll show you, to plug in this core efficiency into the model, right, to predict the star formation efficiency. This is very preliminary, not published yet, but what we're doing, at least as a first look, is taking all these local clouds we have their power law slopes, we have their Mach numbers, and then we don't have their driving parameters that will set the width of the PDF. And we have some estimates of the mean density and so forth. And we have our empirically derived feedback factor, but we can plug in their properties into our model, right? The star formation rate theory. So what our theory would predict based on this information, and compare that to their actual observed YSO star formation rates. And of course, it's not perfect, but I think it's done a lot better than just the pure lognormal models, the generation before it. And it'll be exciting to see how much this efficiency factor maybe varies between these clouds, if that can maybe explain the scatter between our theory prediction and the observations. But this is a promising first step for getting one of these models really nailed down. With that, I will end. And so I'll put up a few points from observations, numerical simulations, and then the analytic model that I would like you guys to take away here. And I'll just flash it up there and then take questions. Thank you.
Excellent talk, Blakesley. Questions? Yeah.
Take the microphone.
Thank you for great talk and impressive work. So maybe you said, but I couldn't maybe follow, but is feedback strong enough to keep the turbulence, or do you still need to drive the turbulence for a million years? If you need to, what is the origin of it?
Yeah, so in the simulations I showed you, we drive continuously on the large scales. The feedback, at least the jet and wind feedback alone, only can get you out to maybe like 5 parsecs or so in terms of its effect on the global cloud properties. It doesn't seem to be able to drive like the giant molecular cloud scale, like 10 parsec and up kind of turbulence. For that, you could get to rely on supernova feedback to do that. Certainly can get you turbulence on scales of 100 parsecs. And then, in Mike Grudic's simulation that I showed you, where the cloud just completely evaporates, right? So that's even going out to the 50 parsec scales once it gets evacuated there. Yeah, so it can do, the jet and wind feedback can definitely do some work in these simulations, but it's predominantly we need to include larger scale motions from larger in the cascade on downward.
So in that sense, it's also related to the star formation efficiency or globally of the galaxy.
Right, yeah.
Hi.
Hi.
Very nice talk. I really
you.
enjoyed it. 2 questions. One is, many years ago, saltpeter predicted a mass distribution function for newly formed stars, which I think has been pretty much verified, if I'm not mistaken, for main sequence stars. I don't know about very low mass stars, but 2 things. One on that. One is, you think you'll be able to predict or test the saltpeter law? And second, the saltpeter law and its observational, the observations that confirm it, sort of, can be used to tweak the models that you're doing right now, and that might improve the, your models.
Yes.
That was question 1.
Yeah, that's definitely, there's already been a lot of work for the mass function with these kinds of models, for especially the lognormal models. There's probably 20 papers predicting that. The problem there is that the fragmentation in the isothermal limit will never stop. You'll just keep fragmenting forever. And so you need like some sort of thermal physics or the feedback physics to set the low mass and high mass ends of that. So I think for this analytic model, we could definitely make some predictions, but again, we would need to have that core efficiency factor understood before I would really trust them.
Okay. Second, stars form in clusters, typically very tight clusters. So formation is very close to, stars are formed close to other stars, which may form earlier. And one of the pictures that you showed was the Eagle Nebula
Mhm.
with the so-called pillars of creation, where you see star formation on the outer edges of these dark molecular clouds. And in addition, there's a huge amount of ultraviolet and X-ray radiation, which is converting the molecular material into atomic
Atomic,
material. So I'm wondering whether your models are missing the physics of the dissociation of the molecular material into atomic material, which will change things.
They are. And in fact, the observations are missing it too. And I'm really glad you asked that because this is something I'm really interested in. So our analytic model assumes there's some compression that's driving these supersonic motions. It could be triggered star formation, like that's probably happening in the Eagle Nebula. But after that point, it's kind of silent about the phases. There's some gas, it's above a critical density. It's going to be molecular just because, you know, you're past the 10 to the 21 centimeter -2 transition from atomic to molecular gas. I think there's a lot more that could be said about that. And so something I'm working on right now is a mid-X proposal for UV spectrograph that will look at the H1 to H2 dissociation fronts and connect that to star formation. So this is a proposed mid-X telescope called Hyperion. Erica Hamden at Arizona is the PI. And this is essentially what we want to try to target is understanding how H2 is part of this picture. So the dissociation of H2 as compared to the star formation rate, or the formation of H2 compared to the star formation rate. You can divide the cloud into these regimes of where it's growing, rapidly star forming, cycling gas between atomic to molecular, and then finally the party ends with feedback, right, with supernova feedback, et cetera. So that dissociates the cloud back into atomic gas. So, you know, I think there's a lot more we could do with this kind of model to connect it to the life cycle of molecules in the star forming region. And, you know, having new observatories in the UV will be key for that. So, no, don't say it, but yeah, it's true.
When you included, hello, by the way, great talk. When you included the feedback, you created a tail on the left side of the distribution. Do we observe these tails?
So yes, but if you ask the observers, they'll tell you we can't really trust the very low column density regime, especially in dust observations, because there's a lot of, you know, there's foreground problems. There's boundary, like where do you draw the boundary at these very low column densities? You can't close the contour in the observations. So they will, you know, there are some people that say they can't even really observe the log normal at all when you're looking at dust. And dust is nice because you get a wide dynamic range in column density. So you can also do this with gas tracers, but then you're dealing with radiative transfer effects. There's other complications with gas. So unfortunately, it seems like we can't really observe the lowest column densities there just because of observational bias.